Hey there, students. If you're just joining us, this is a production of the Oregon Curriculum Network, which you can dig down into it. You'll find things called the Digital Mathematics Curriculum. You'll find a website at 4dsolutions.net. You may or may not find these things depending how long in the future we are and what's still out there, but at one time 4dsolutions.net and currently at the current time was a little bit frustrating to get into because where's a link here anywhere? It looks like just a logo. So you click on the logo. So it says it's a pioneer in open source, and yet there's kind of these tricks. So if you've clicked on the logo twice, then you get to sort of a headquarters in the sense of it points you to a small business in Portland, Oregon that has a cyber footprint and has for quite a long time in the form of blogs, GitHub, the usual things that digital citizens of the internet these days have. It's not unusual. The kind of racism has been a topic, by the way, and other humanities topics. So this is not a purely STEM curriculum. We look at philosophy and difficult topics, and so sometimes I'll dive into something, you're like, hey, I thought this was a math class. Well, not exactly. But in the calculator of tomorrow, though, I do want to show you, I've read about this feature, but I haven't done a lot to use it. You can paste, I've started a new untitled notebook over on the left, and I have my Gimpy 2 version of the random Tetrahedron notebook on the right. Now I refer to those with great familiarity as if you're supposed to know what I'm talking about, and if you're just joining us you probably do not. But I'm talking about using high precision numbers, like they're not just floating point numbers, they have precision of 200 bits in this case, and I've been playing around with those vis-a-vis a certain tetrahedron that I would generate at random. And I'm going to do something similar here, so this is going to seem like a math class. I'm going into tetravolume.py, which is one of the tests at my repo, and there's a test Martian. And it's one of the unit tests that comes with that module, kind of showing off what that module can do. So if you just import tetravolume.py, it's not going to touch the tests. It's not going to run the tests. This is a common pattern in Python where if you ask it to run top level as somehow the main thing, then you can either make it do useful work or you can make it test itself. Like I can pass in I can pass in the 6 edges of a tetrahedron on the command line and get back an answer. Let's see that. Let's see, do I know how to do that? Well, of course, with the regular tetrahedron, all the edges are the same length. So let's actually go out to the command line here for a second. While it's getting ready, though, I'm going to cut and paste the Martian math source code to untitled. In case, did I paste that? Yeah, so I need to shift it over. We can still call it test Martian, that's fine. And now the question is, do I have enough? Let's just assert something. See, assert is a built-in with Python, so I don't need to worry about that. I'm going to assert that the results here is 20. So I'm going to assert the following, and assert is a keyword, and no keyword takes arguments. That's a rule of a keyword. It doesn't eat. So you can put parentheses after assert, and it's not going to crash because, you know, parentheses in general are a pretty innocent thing to add to your expression, but you can look like you have an accent in Python if you put a parentheses where they don't need to be. Now, I'm not sure if this is going to work really. First, I'm going to see if it just eats it, takes it as a definition. Now I'll just call it test Martian and see what happens. I see another problem. I don't have a self anymore. I'm outside of any class. So take that out and run it, and it raised, okay, Q vector not defined. That's because although I've been cutting and pasting these things over, they don't necessarily have a presence in the namespace yet. I have to run everything, just make sure. No, make tet is not defined. So yes, there's a make tetrahedron thing, and I believe it lives inside of tetravolume, so we'll bring that in as well and go back and rerun this again. Make sure I run this import and try it again. And this time the insertion is simply incorrect. So let's just return result 0 and see how close we are. Return results. Let's not make it an assertion. Let's just say, hey, show me the answer, please. So redefine and run. And okay, so it's almost 20. And the second volume, what is that? What am I even looking at there? Oh, I've returned also the IVM volume, or XYZ volume. So I'm returning IVM and XYZ volume. So now we're going to do the same basic thing, except we're going to use ABC as my coefficient. So instead of 522, we're going to put ABC as my coefficients. And I'm going to make ABC be real numbers in the sense of 200 bits of precision. Now those aren't really real numbers. I'm referring to them as real numbers. So let's just say X, Y, Z. These will be 3 edges of a tetrahedron, all coming from the same origin and going to the corners of a regular tetrahedron. You can think of a tetrahedron pointing upwards on the sand. In fact, let's see how fast I can get to Martian Math Storyboard Flickr. Does that take me right there? And DuckDuckGo, checking the search engine. Let's just give it a shot. Looks like we're in the neighborhood. Sorry. Martha Math Educator. This is a blog post in control room, but my guess is it's going to take me right there. I can probably just click on any of these and find myself in the album I'm talking about, and that'll get me to the picture I'm talking about. So this is called knowing your way around in your own neighborhood. Like if you create a lot of websites and you want to maintain them, it's good to know where things are. And I've been adding to this Flickr photo stream for a long time, so I know where things are there. And when I go to Storyboard Martian Math, which is the album I'm looking for, I know that I can find this particular picture of a tetrahedron filling up with water. So we're going to pick X, Y, Z as 3 vectors pointing in these 3 directions and see what the product is and see what the volume is with those 3 inputs. And remember, this is tetravolumes, right? So I'm expecting just to have to multiply those 3 numbers together. 5 times 2 times 2 is 20. That's why I expected 20. But now I'm going to use these higher resolution numbers. So let's see, what's an easy way to do that? I guess we can just say MPFR and we'll do 5. Now I think the context is such that they're automatically going to be 200 bits of precision, and I do see that typo. Going back to fix that. So MPFR is the multi-precision real number type offered to us by the Gimpy 2 module, which is free open source, and I've installed it recently in the sequence of videos here. So there's my XYZ. Now I'm going to test Martian XYZ and pass that on up to the function already defined. These are integer coordinates, but in being multiplied by high precision 200-bit numbers, we should get to keep our 200-bit numbers in that way, because integers don't destroy them. Integers merely scale them. Because integers are, you could say, as precise as they get. They're already infinitely precise, we could say. Let's stop talking and see if I'm right. So I just get an error. Takes 3 positional arguments, 0 positional arguments. Oh, I don't think I've redefined it yet with the ABC, and so test Martian here would now not work. So if I go back to integer numbers, 225, what do I get back? I get back same precision as before. Now I'm going to try that same experiment with these super high precision numbers, and there I'm getting 20 back to way far out in zeros, and then 119 at the end, right? So I would say I'm pleased with the precision I'm getting, and this is just the kind of little exercise you might want to do. Let's go to 300 bits of precision and run this again. I don't really need to redefine test Martian because precision is not going to change in that respect. And run it again, and run it again, and now it's 20.0 out to 300 precision. So instead of 5 times 2 times 2, let's do 3 times 3 times 3. What if all the edges of our tetrahedron are 3? We would expect 27, right? It's not, I was going to say it's not computer science, but of course it is. We could say, or it's Martian math. So that's 3 times 3 times 3 is 27, 4 times 4 times 4 is 64. So these are the third power sequence, but not modeled as a cube, you will notice. And that's one of the trademark features of what I call Martian math, which is a wrapper around the Bucky stuff, synergetics, etc. Late 1900s published. We've been through it. We'll keep going through it. Hope that was elucidating. And I don't think I'll throw this up on GitHub. Just remember, it's what one of these unit tests is focusing on in the tetravolume world. And you can use higher precision numbers with such tests should you so choose. All right, talk to you soon.